Welcome back to another explainer. Look, if you're gearing up for your board exams, you already know that linear algebra is an absolute massive pillar of your math curriculum. But right in the middle of that pillar is a specific concept that kind of acts as the gatekeeper to those really high scores. I'm talking about the determinant. So today, we're laying out a highly structured, step-by-step game plan to conquer determinants completely. We're going to treat every single formula and rule not as just some random thing to blindly memorize, but as a strategic tool to help you absolutely crush those complex, high-weightaged exam questions. Let's get into it. Okay, let's dive into this roadmap. First up, 1. Demystifying the determinant. Next, 2. Core properties you must know. Then, 3. Minors, cofactors, and adjoints, which leads right into 4. Calculating the inverse matrix. And finally, 5. Solving systems of equations. All right, starting with section 1, demystifying the determinant. Think of this as laying our concrete foundation, right? Every single concept we cover from here on out is going to build on this. At its core, a determinant is just a number. It can be real or complex, that's tied to a square matrix. It's kind of like the matrice's own unique mathematical fingerprint. But right off the bat, we need to talk about a classic board exam trap. Look at the notation. You see those two vertical lines around the A? They look exactly like the absolute value symbol. Do not fall for it. In matrix algebra, that notation is strictly read as the determinant of A. So if your matrix has negative values, your determinant can absolutely be a negative number. Don't go stripping away the negative sign thinking it's a modulus, or you're going to lose really easy marks. Oh, and remember, only square matrices even have determinants to begin with. So let's start simple and build our way up. The most straightforward example is your standard 2x2 matrix. If your top row is A and B, and your bottom row is C and D, finding the determinant is literally just cross-multiplication. You multiply the main diagonal, so A times D, and then you just subtract the product of the other diagonal, B times C. AD minus BC. It's quick, it's elegant, but hey, don't let the simplicity fool you. Mastering this basic 2x2 formula is totally non-negotiable because you're going to need it as a stepping stone for those massive 3x3 matrices you'll definitely see on your exam. Moving right along to section 2, core properties you must know. Picture this, you're sitting in the exam hall, the clock is ticking, and you're staring down this huge 3x3 grid of complex numbers. Calculating that determinant the long way is going to eat up so much of your precious time. Well, these properties, they are your cheat codes. They literally turn a 5-minute grind into a 5-second observation. Let's run through this rapid-fire checklist. First, transposing a matrix, flipping its rows and columns, doesn't change the determinant's value at all. Second, if you swap any two rows or columns, you just flip the sign of the determinant. Third, and pay attention because this is a massive time saver, if you spot two rows or columns that are identical or even just proportional multiples of each other, stop calculating. The determinant is instantly 0. Boom. Done. Fourth, multiplying a determinant by a constant k means you're only multiplying one single row or column by k, which is super different from standard matrix multiplication. Fifth, if plugging in alpha for x makes the determinant hit 0, then mathematically, x minus alpha is a factor for sure. And finally, if you've got a triangular matrix where everything above or below the main diagonal is a 0, your determinant is literally just the product of the numbers on that main diagonal. Simple as that. Now, these properties are absolutely incredible for speeding up your algebra, but it does bring up an interesting question, doesn't it? We're shifting all these numbers around a grid, but what does this actually mean out there in the physical world? Like, how do we actually use this abstract algebra in geometry? Well, as it turns out, determinants are pretty much perfect for calculating geometric space. And you'll definitely want to lock this away in your memory because finding the area of a triangle using determinants is a classic high-frequency question on board papers. So if you have a triangle on a coordinate plane with 3 vertices, you can find its exact area by setting up a 3x3 matrix. Your first column is all your x-coordinates, your second column is your y-coordinates, and your third column, you just fill it straight down with the number 1. You might be wondering, why the 1s? Well, remember, our very first rule. Determinants only exist for square matrices. Those 1s just fill out the grid so we have a nice, perfectly square 3x3 matrix. You take the determinant of that whole thing, multiply it by half, and there you go. You've got your exact area. All right, stepping it up a notch. Section 3, minors, cofactors, and adjoints. We're moving up the ladder into the operational mechanics now. These are the heavy lifters you're going to need for those long answer, high weightage exam questions. Getting this down is non-negotiable. So let's look at them side by side because students mix these up all the time. A minor for any specific element is what you get when you literally cross out the entire row and column that element is sitting in, and then you just calculate the determinant of whatever numbers are left behind. Easy, right? Now, a cofactor is almost the exact same thing, but with one absolute crucial step added. If you compare them visually, the only difference is that -1 to the power of I plus j. All that little formula does is create a checkerboard pattern of alternating positive and negative signs across your matrix. So simply put, a cofactor is just your minor but with a specific plus or minus sign slapped on it, depending entirely on its exact address in the grid. Okay, so once you've done all that painstaking work to calculate the cofactor for every single element, you take all those new numbers and arrange them into a brand new grid. That's your cofactor matrix. Now, to find the adjoint of the matrix, you literally just take that cofactor grid and transpose it. You flip it so the rows become the columns. And that's the whole shebang. The adjoint is literally just the transpose of the cofactors. Which brings us nicely to section 4, calculating the inverse matrix. Now, what's really interesting here is that everything we've talked about so far, the determinant, the minors, the cofactors, the adjoint, they are all combining right here to solve one major problem, finding the inverse. But hold on, before we do any math, we have to check a strict mathematical law to see if the inverse even exists at all. If you calculate the determinant of your matrix and it's exactly 0, that matrix is what we call singular. And a singular matrix is fundamentally not invertible. No inverse exists. You just stop right there. An inverse is only possible if the matrix is non-singular, which just means the determinant is literally any number other than 0. So let's say your matrix passes the non-singular test. Awesome. Here is your foolproof recipe for full marks. When you're in the exam, this is the exact chronological algorithm you want to write down on your paper. Step 1, find that determinant. Step 2, calculate the cofactors for all your elements. Step 3, transpose those cofactors to get your adjoint matrix. And step 4, multiply that adjoint by the fraction of 1 over your determinant. Actually, take a close look at step 4. See that? That is exactly why a determinant of 0 breaks the whole system, because you can never ever divide by 0. Finally, the big finale, section 5, solving systems of equations. We've reached the absolute climax of the chapter. This is the ultimate practical application. Like, why did we spend all this time learning to find the inverse of a matrix? So we can solve multiple linear equations simultaneously and do it with incredible efficiency. If you're staring at 3 separate equations with 3 unknown variables, x, y, and z, you just plug out the coefficients and build a matrix called A. Your variables, they go into a nice, neat column matrix called X, and your constants drop into matrix B. So the crucial takeaway is that we're translating standard, messy algebraic equations into our sleek new matrix language, A times X equals B. Now, to isolate X and actually get your answer, you can't just divide by matrix A. Matrices don't work like that. Instead, you multiply both sides by the inverse of A, and that gives you this beautifully elegant final solution. X equals the inverse of A times B. Of course, we all know board exams absolutely love to test the edge cases, right? Which brings us to evaluating consistency. Honestly, I'd highly recommend just memorizing this logical flowchart because it's a guaranteed high-yield topic. Here's how it works. If the determinant of A is anything but 0, your system is consistent and you've got one unique solution. Easy. But if the determinant is 0, you have to do a little more digging. You need to calculate the product of the adjoint of A multiplied by matrix B. If that product is not 0, your system is inconsistent, which means there's literally no solution, period. Now, if both the determinant and the adjoint B product come out to 0, well, the system might be consistent with infinitely many solutions, or it could be inconsistent with none at all. It varies. Wow. Okay, we've covered a massive amount of ground today, right? We went all the way from basic cross-multiplication to solving huge 3-dimensional systems of equations using adjoints and inverses. But before we wrap up this explainer, I want to leave you with a final thought, something to really push your understanding beyond just rote memorization. We just saw that a singular matrix can sometimes result in no solution to a system of equations. But really think about what that actually means. If these equations represent lines or planes, what does no solution look like geometrically when drawing those lines in physical space? I'll let you ponder that visualization as you prep for your exams. Keep practicing those core properties, watch out for that absolute value trap, and you are absolutely going to master determinants. Good luck out there.